In the previous video, I did a basic introduction on how to model a pandemic. And in this video, we will focus specifically on the parameters that we'll be using in this project to model it. Now, as I said before, this is a gross oversimplification, which means that the numbers and the things that we model throughout this aren't things that we can precisely say are predictions, but the principles behind them, the ideas, are actually things that do work out in the real world. So let's go ahead and get to it. Okay, first of all, last time we had a very basic start. Let's start with y being the number of infected persons, and x was being represented by the number of, and I was just calling them like rounds of infection. We'll actually change that today. And then r was this rate of transmission, or the reproductive number, and we called it r naught. Our basic equation was simply that y was equal to r naught to the x power. Every time that this disease spread, you were multiplying by its reproductive number. But this obviously is way too simple. This assumes that basically there's an infinite number of people and they can continue to get infected. So we took this equation and we came up with a new number, which I'm going to represent with here, which is p, which is the percentage of people not infected. This was key because if you were infected, you could not get sick. And so we modified this one step by saying that y was equal to r naught times, okay, whatever this p number was. And I'm going to go ahead and substitute here. P is a percentage, so that is actually equal to 1 minus the total number who are infected, so that's y, over the total number of people, which I'm going to use a capital T, and now I got a new thing called total population. And so this percentage of people not infected is 1, which is 100%, minus whatever percent are infected, and that percentage is y, which is the number of infected persons, divided by t, which is the total population. Okay, so let me take it one step further there. So now I've got y is equal to, and there's actually a next step here, because you can actually take away another percentage of the population through social distancing. So you're basically taking people and making them as if they can't get sick, even though they haven't been infected already. The same thing goes if you were to get immunized. You have more people who are unable to get sick. Okay, so what I'm going to do is I'm going to use the capital letter S for the percentage of people social distancing. In short, S is just going to represent the percentage of people who can't get the virus and can't spread it. And so here we go. We go y equals r naught times, and then this is a percentage. 1 is 100%, and then we take away the percentage of people who are already infected. That's this y over t. And we take away the people who are social distancing, either physically or eventually if we get a vaccine or whatever, the number of people who can't spread the disease, the percentage of people who can't spread the disease. And so that reduces our rate of transmission. Okay. There's one more thing that we need to add in here that was not in the last video, and that is basically where are we at right now? What is the current number of cases? Because this equation as written actually starts as if you had one infected person, but that's not where we're at. And so what you would do is the more people who are infected, the more people who can get infected from that group of people. And so it's actually a multiple here. And so our final equation looks like this. So the number of infected persons, y, is equal to the current number of cases, infected persons, times, and then in this whole parentheses is this reproductive number, the rate at which this disease spreads, and then times a percentage of the people who can actually still spread the disease, because it's 100% of people minus the people who are already infected minus the people who are social distancing leaves what percentage of people can spread the disease. Okay, and now I know that there are going to be people in the social distancing category and who've already been infected, but we're going to keep those as separate categories for the math. So in case you were thinking about that, we're just going to make it simple. We need to do one more thing. This X right now represents something very odd, which is the number of rounds of infection, which is kind of a weird thing. I'd like it to represent days. But in order to do that, what I need to do is have some sort of factor to counterbalance the fact that this rate doesn't happen in one day. You don't get sick and spread it to 2 other people or 3 other people in a single day. It takes some time. And so now I'm going to bring in a new thing, and this will be our last one, I promise. And this is the number of days to spread the virus. In other words, how many days does it take to get sick and to spread the virus? And so what we're going to do is we're going to take our x here, and we're just going to divide it by however many days that takes on average. And then now x can represent days, and this equation is completed. All right, now all of these coefficients, as we would call them, C, the current number of cases, R, the reproductive number, T, the total population, S, the percentage of people of social distancing, and D, the number of days it takes to spread the virus. All of these things we're going to kind of represent as fixed values, although there are some fluctuation, and we don't actually know the exact values in every case. And so there is some sort of gray area in our estimations as we go through this. But this is actually going to give us a pretty solid understanding of how diseases spread and what factors, which one of these things can we affect to actually slow down the rate and have less people infected and therefore less people die. And the great thing is that Desmos is set up to do this type of equation without us having to do a bunch of extra work. Let me show you.